Okay, so our next speaker is Bartosz Bielawski. Did I get that okay? He is a computer engineer who has been working at CERN since 2012. For the last 3 years, he's been working in the beams department, radio frequency group, writing software for hardware controlling various RF systems, mostly for the LHC and the new linear accelerator, LINAC 4. Thank you, Bartosz.
Okay, thank you. Good afternoon. Today I'd like to tell you about a system that we have built to monitor some analog signals, mostly in the LHC, but in the future maybe also in the other machines. First, I'll tell you about the solutions that are already available at CERN, what can be used, how can we plug new analog signals into the existing system, and about also the systems that are provided by different equipment groups at CERN. Then I'll tell you about the system that we have upgraded to bring it more into the, to integrate it better into the current control system. Then I'll explain why we decided to have some custom solutions instead of having something really standard. Then I'll tell you briefly about the system itself, and at the end I'll describe what are our future plans. Okay, good. So the most well-known system for acquisition of analog signals at CERN is OASIS, which is provided by Beam's Department Controls Group. And this is really a big system which has a lot of capabilities. It is able to acquire signals of different frequencies. It's able to do it on many channels. It has support for many different types of hardware. It's all integrated into the rest of the control system. It means that there are applications for the users to be able to monitor the signals, to record them, to switch the multiplexers if there are more than one signal sharing the same channel in the hardware. Unfortunately, it's also a bit complex. And because it requires a lot of specific hardware like VME crates and the payload cards, it's also kind of expensive if you do not do a full deployment of many signals. On the other hand, each of the groups tries to deploy something that is built by the group themselves. So usually these are some acquisition buffers that are built into the hardware itself. For example, in the RF group, we have this approach in which the data that is already acquired by the cards that are controlling the cavity loops is also stored in the memory, and using a common interface we can easily extract this data and just to do some processing, just for monitoring. We also have a high-speed monitoring system that is called OBSBox that is meant to monitor the longitudinal properties of the beam, but this system, contrary to the previous one I have described, it's really specialized. It's meant to run at the full speed, monitoring each of the bunches separately. And as such, it needs a specific hardware and the servers that are running with things like 128 gigabytes of memory just to be able to collect all the data and store it in the memory for processing. The original system that we had in LHC was meant to monitor some critical signals in the LHC. Of course, all of those signals are interlocked. That means that, for example, if the amount of power that is reflected back from the cavity towards the klystron crosses some level, there is an interlock and the beam will be damped. But in many cases, we are not able to monitor what was really how did the waveform look like. And in some cases, it's worth looking at those signals, because if we see that there is power that is reflected in some specific pattern, or maybe we see that there are arcs in the klystron that are being lightening up, it may mean that the klystron is, for example, approaching end of life, and such operation of replacing a klystron should be planned in advance and carried when we have time to do such thing. Otherwise, we could cause stop of the machine for even several days when we have to unplug this old klystron and put the new one. And we already had a system, but unfortunately, it wasn't enough reliable. So basically, it consisted of a Windows XP PC that was running in the technical network. And we kind of often found out that it was shut down for an unknown reason. And even if it was running, then the software that was running on the PC kind of often was not working. So even if we wanted to debug the accelerator, we often found out that there were no traces of things that were happening. And also it used some custom USB to Ethernet bridge, which had drivers only for Windows. the device that was doing the acquisition is a Picoscope 6000 series oscilloscope from Pico Technology. Well, now, why we decided to use some custom solution instead of using Oasis that is well known and everybody uses that? Well, we had some special requirements. First, this system that monitors the current consumption by the klystrons is placed in high voltage bunkers that are at 0.4 in LHC. Those bunkers, they are probably like 2.5 times 2.5 meters, so they are pretty small. All the big cylinders you can see here, they're actually capacitors that are supposed to even out all the ripples on the power supplies, and they are fed with 60 kilovolts. Each of the klystron is consuming about 8 amps of power, which brings us to about 300 kilowatts per klystron. Now, what happens if we have an arc in the klystron? Well, it starts to draw way too much power, and it can burn the device. And because usually there is not enough time to turn the power supply to turn off, to safely shut down the operation, we have to do something faster. One of those cylinders is actually a thyristor that is connected in parallel with those capacitors. If we notice that one of the klystrons starts to consume too much power, we basically just short-circuit the capacitors to the ground, causing like a huge discharge. And after this operation is done and we are safe, then we start to analyze what had gone wrong. So basically, we don't need many channels because we have 4 klystrons plus the capacitor current in total per one of the bunkers. And we don't have much space in it. And what's even more important, for most of the time, nothing really happens. So it means that our acquisition system may be waiting for 2 weeks, maybe 3 weeks, doing nothing. The scopes are armed and waiting for the signal to happen. That would be a waste if we had to deploy a full system that is able to do thousands of or millions of acquisitions per second. I mean, something, and then doing these acquisitions every cycle like we have it at CERN, in this case. That's why we decided to do something custom. There is one extra thing. We had a request from the arc monitoring that we can trigger the system from any of the channels. Because to do to each of the scopes, you have connected 4 channels, and each of those inputs should be able to trigger. As far as I know, Oasis does not have such capabilities at the moment. Well, the hardware. So this is already the description of the system as we have upgraded, after we have upgraded it. So basically the scopes are the parts that we already had. We had the PS6000 series. These are USB-enabled scopes, so they were connected to that bridge at that time. And our upgrades, during the upgrade, we decided to bring a standard small PC, for example, Control Keys or Intel NUC, one of those small industrial PCs, just to have something standard that is able to run SLC6 or CC7. These are CentOS-based distributions that we use at CERN. Then also, sometime later, we have decided that it would be better if we have other signals that don't require that much bandwidth to use some simpler scopes, and that's why we have added also support for PS3000 family. In the small table, you can see that the vendor that produces those scopes, they actually have two other families. This is PS4000 family, which doesn't have that much bandwidth, but you can get more bits out of the measurement if you need it. And there is also a PS5000 family, which connects, which kind of integrates both features from the PS3000 and PS6000 families. That is more bits and a bit better bandwidth. The software part. The manufacturer kindly provides not only drivers for their own devices, but also a full SDK that is done in C, and a set of dynamically linked libraries, which is pretty great because it's easy to plug them into the system that is already running. And fortunately for us, they have decided not to rely on drivers integrated into the kernel. They are relying on libUSB. libUSB is a project which aims at providing an abstraction layer to communication with devices from the user space level. This means that we are not relying directly on the API from the kernel, and we can just build our software on top of the existing layer of libUSB. And then, of course, also there is the software that is just provided by the vendor, just if we wanted to do some measurements without really going into details and using some advanced capabilities. For people who are using LabVIEW, yes, there is also a LabVIEW interface, although we have decided not to use it and just integrate it as a FESA class into our control system. There is one small problem with the current versions of the driver from this vendor. Unfortunately, they have decided to make a C library, and the enums and defines are differing between different families of the scopes. That's why I had to write a simple wrapper library that allowed us to talk to those scopes no matter which family where they're from. And as a bonus thing, as we already had this hardware abstraction library, I have decided to use Swig. Probably most of you know it already if you're doing some stuff with scripts. Swig is a simple tool that allows to wrap C++ and C code into many other languages. This creates bindings for things like Ruby, PHP, Java, and Python was one of the things that I have wrapped the library into. Now, here we can see there are two examples of how the software was actually used. So the image on the top was creating, this interface was creating using a tool called Inspector. It's also designed in the other group. This is a Java interface that allows you to easily drop controls onto the form and connect them to underlying Feza devices in CERN's control system. On the other hand, the screen that I captured for the bottom picture, this is something different. This runs directly in Python, directly over the HAL interface. And this shows us that we can do some diagnostics and check the state of the scopes, even if there is nothing available except for the library and the scope connected to the computer itself. It means that if we, for example, wanted to do some calibration of some devices, it will be really easy to connect those scopes to PCs and write some software that doesn't need any user interface except maybe a few command line arguments that you want to pass when you start the process. At the moment, we have deployed permanently 16 of those scopes, and they are connected to 8 computers. Some of them are monitoring some of them are monitoring the crowbar events that are short-circuiting the capacitors, and some of them are monitoring the arc detection in klystrons. All of them are in LHC. We have also 2 scopes that were deployed as debugging helping tools that are connected to the reflected power in the LHC when we were not sure what's the waveform, and we wanted to gather more diagnostics of the system. So here you can see how the system looks in the high voltage bunker. This is just a small PC connected to the Ethernet and to the power, and then on the other side there are 2 USB scopes connected. The scopes are below. For the future plans, well, for us the system is complete as it is. But if there are some clients who would want to add more families, we would be glad to add other families to the hardware abstraction library. That wouldn't change many of the software that is on the higher levels. That would just require adding new class that just can handle this specific scope. Then we also thought about being able to deploy a simple system consisting of a computer and the scope itself, enclosed in a box that could be dropped anywhere, connected to the network, and then configured to do some measurements, and then removed as soon as the problems are gone and be deployed somewhere else. And of course, when I was actually writing the hardware abstraction library, I looked at the API of the Oasis, and I made it similar, so it shouldn't be really complex to integrate those things together, and let Oasis users use the cheap oscilloscopes. Well, yes, I guess that's it. So thank you for the attention.
So quick.
And in RF, high power RF conditions, how to avoid noise come from some kind of AC adapters of power line?
We don't have this kind of problems. I mean, in this case, I guess that the scopes have good enough power supplies, and basically the klystrons are powered from DC. This is 58 kilovolts, but this is DC, so we don't observe any problems with it. The scopes themselves, the inputs are 50 ohm loaded, so there is the loading, the resistance is matched, so we don't have any problems of this kind. Any other questions?